Welcome back. So we've been talking about earthquakes, where they occur, how they occur, what they release energy in the form of seismic waves. Now we're going to talk about the Earth's interior. It's something we talked about back in Unit 1. Different layers of the Earth. The solid inner core, the liquid outer core, the mostly solid mantle, and that very thin solid crust on the outside. But how do we know that? How do we know that's there? That's a good question. Well, guess what? We used earthquakes, specifically seismic waves, in order to help us figure that out. So, before we proceed though, let me go ahead and give you another part of the super secret code. It is the number, 0. You got that? 0. One more time. 0. Okay, so, Earth's interior. We can't directly study the Earth's interior. We can't go down there. In fact, the furthest we've ever gone as humans is only a few miles down into the Earth. And that's it. It becomes too hot. We can't go any further. Machinery tends to break down. It gets hot, things melt, whatever. So we can't really study it directly. So remote sensing is the technique that's widely used in geology and what helped us figure out what's inside the Earth. So, looking at seismic waves and how they travel through the Earth is one of the best methods to analyze Earth's interior. Because remember, P waves, primary waves, they're a compressional wave, and they can travel through solids and liquids. So P waves can radiate through the Earth, all layers. Whereas S waves, secondary waves, are shear waves, and the sheer physics of them prevents them from going through liquids. They can go through solids, but they can't go through liquids. So how can that help us figure out what's inside the Earth? So, for example, in 1995, there was an earthquake in Kobe, Japan. Directly on the other side of the Earth, P waves were detected. However, no S waves were detected. Interesting. And then kind of mapping where P waves and S waves were felt. So the black arrows represent P waves, the red arrows represent S waves. So there is S waves that could be felt from here all the way over here, but this entire portion of Earth, it was in what's called an S wave shadow zone. There was no S waves there. Well, why is that? Well, there must be something preventing the S waves going through, but not the P waves, so there must be some liquid in the center of the Earth. There you go. That's how we know. And again, just the sheer nature of these waves and the physics of these waves, we know that compressional waves can travel through solids and liquids, but shear waves can only travel through solids. So therefore, if something is preventing shear waves, in this case the secondary S waves, from hitting this side of the Earth, must be some liquid in there. We can also figure out how the layers of the Earth based on how the waves are kind of refracted a little bit. Not necessarily, also reflected, but also kind of bend or refracted, because when waves, whether it's a seismic wave, a light wave, any sound wave, when they go through different density mediums, meaning going from like a solid to a liquid, they bend, they change direction a little bit. So by noting all of that, we can kind of further figure out what's inside the Earth. But that takes a little bit of physics involved. But again, using the P and S waves are reflected or bounce off of the liquid outer core, not being able to travel through to the other side. Again, that just goes back to the sheer physics of them. Yeah, so that's how these seismic waves helped us figure out what's inside the Earth. Because, some people, or if you watched a movie, if you ever watched the movie The Core, completely impossible. All right, we can't go down there. We can't even drill down there. We can't send a machine down there. So, what are some other ways to help figure out what's inside the Earth? Well, if we can't go down there too far, maybe we just wait for stuff to come up. So we wait for magma, liquid molten rock, coming up from the mantle. So we can wait for magma. Once magma hits the surface of the Earth, it's called lava. More on that in another unit. But that brings up material from the mantle deeper down in the earth. So we can just wait for samples of that stuff to come up, and then we can analyze it to figure out, what consistency type, what chemical structure, what chemical makeup does the mantle have. So we can wait for it to come up. As mentioned, we can drill down, but we can't really drill down that far to really get into anything. We can't even drill to the mantle. We've only drilled within the crust. So we can't even send machinery down to analyze the mantle, the liquid outer core, or the solid inner core. The mantle material, we just kind of wait to come up, magma and lava, but the liquid outer core and solid inner core, that's way too far away. So, what is the deepest we've ever drilled? Well, quite interesting. So back in the mid 1900s, 1950, up through the 1990s, the U.S. and Russia, then the Soviet Union, was in a Cold War. We stockpiled bombs. We each built bigger militaries under the threat that we would go to war with one another. One of the challenge, there was a space race between us and the Soviet Unions. Not only was there's that space race, but for some reason there's also a race to see who could drill down the deepest. I don't know why. That was a thing. So the Soviet Union and us were racing, and guess what? The Soviet Union won. Hooray for them! Good job on that victory. So the Soviet Union, now Russia. So in Russia, there's a place called the Kola Super Deep Borehole. Again, this was just no other race than just to see who could drill the deepest. Not necessarily, putting anything down there, not necessarily getting readings, which they later did, scientific readings and stuff. It was just to see who could drill the deepest. So they reached 12,262 meters, which is a little over 7.5 miles, and it took them all the way up until 1994, and is currently the deepest artificial point on Earth. You can see the deepest active mine is about 3.9 kilometers. That's about 2.3 miles or so. So that's as far as humans can go before it gets too hot. But again, the Kola Super Deep Borehole, over 12,000 meters, over 7.5 miles. Here's a video I would like you to watch that goes over a little bit more information on the Kola Super Deep Borehole. So, I mean, it's a good feat. It's an interesting feat, but just not one that's really useful. So this is a picture, an old picture of the drill site when it was active. So the drill was housed in this building, and the way it works is that they would kind of drill down, and when the drill bit and pipe got down further enough, they put another pipe on top, drill down, put another pipe on top, drill down, get another pipe, put it on top. So you're kind of just adding segments so you can keep drilling down further and further and further. Nowadays, it kind of looks like this. It's in ruins. You can visit the site. Let me move me out of the way real quick. You can visit the site. This is it. That's the Kola Super Deep Borehole. There it is. So they put a cap on it, so no one falls in, I guess. But yeah, that's it. That's where the deepest hole on Earth is. You can see it's in disrepair now. Yeah, it's in the middle of nowhere, northern Russia, up near Finland, Norway, and Sweden. But yeah, there it is. Nice fun family vacation. You know what? Let me give you another super secret part of the super secret code. Number 2. You got that? The number 2. One more time. The number 2. All right. So when we come back, I believe we will be looking at our last section, how we measure earthquakes, talking about some of the different scales, the way we measure them, etc. I'll see you back here in just a minute.